This is the first lecture in our second quarter of general chemistry. In this lecture, we'll be talking about thermochemistry, which for everyone taking this class should be a review. And if you took my class in the first quarter, the slides will look really familiar. So I'm probably going to go through this a little bit quicker than I would a normal lecture, just because it is review. If it seems fast, you'll have these slides to look back on, to look over the notes. So just bear that in mind. All right. So what we'll be going through today is really all of Chapter 6, and hopefully I'm picking out the parts that are the most important in Chapter 6. A little overview of where the class is going to be going. There will be 2 exams in the class. The first exam will be covering Chapter 6, which should be review. Chapter 20, which is thermodynamics. We'll talk about entropy and free energy, building off of Chapter 6. And then Chapter 17, which is an intro into equilibrium. All right. Then from there, we'll apply equilibrium to acid-base systems and also ionic compounds in solution. Okay, and then the final, it'll be cumulative, so we'll cover all the material from the quarter, as well as Chapter 16, kinetics. Okay, so overview of Chapter 6, 6 sections. Okay, the first thing we'll be talking about is forms of energy and their interconversions. Okay, remember there are 2 types of energy, and this is maybe more important for like a physics class, but there's potential energy and kinetic energy. Okay, potential energy is the primary energy in chemical compounds. Okay. All of this stuff here, can be converted to work, and depends on how high something is off the ground. You don't really need to know that for this class. Kinetic energy, this is due to the motion of an object, and so the kinetic energy is 1/2 times mass times velocity squared. That equation comes up every now and then in general chemistry, but probably more honestly in the first quarter. At the molecular level, kinetic energy is the movement of the molecules or atoms, if you're looking at atoms. Okay, and this is primarily due to temperature. Okay, the mass and the velocity of the particle obviously make a difference, but the temperature, you're not going to change the mass of a particular molecule, right? But you can change the temperature, and as temperature increases, the motion of that molecule will increase, and therefore the kinetic energy increases. Okay, potential energy at a molecular level, you can kind of break it down into electrostatic interactions, and that is based off of Coulomb's law here, where we have the energy of the electrostatic interactions is equal to the charges multiplied by each other divided by the distance between the charges. Probably never have to use that equation in this class, though. Okay. So if we describe energy transfer, this is kind of important to note. Okay, when we're talking about the transfer of energy, and we'll be dealing with this in Chapter 6 as well as in Chapter 20. It really helps to define these terms. Okay, system, that's the part of the universe that we're focusing on in the problem we're looking at. Okay, there's different types of systems: isolated, open, and closed. Okay, the surroundings are everything in the universe that is not part of the system. Okay, and system plus the surroundings equals the universe. So the universe is really everything. Okay, the system is just the part of the universe that we're interested in for our particular thermodynamic measurement. So if we have a case where we have an initial state that has a high energy level and the final state has a lower energy level, right, that obviously the energy of that system is decreasing, okay? And the change in energy, therefore, is going to be negative of that system. Okay? The energy doesn't just go away, it's released into the surroundings. Okay? Remember, system plus surroundings equals the universe. Okay. Right, in the other case where you could have the initial state of our system be lower in energy than the final state, therefore you have to be increasing in energy. That system, the delta E of the system, is going to be a positive value. That energy has to be coming from somewhere, right? And that's energy absorbed from the surroundings. And we can write a delta E, or really a delta anything, in terms of the final state minus the initial state, okay? Or in chemistry, that would be the products minus the reactants. So we'll see that motif again where we have a delta, in this case, in chapter 6, it'll be a delta H, change in enthalpy, and that's going to be the enthalpy of the products minus the enthalpy of the reactants, okay? So it's, when you're looking at the change in something, it's always final minus initial. That brings us to the first law of thermodynamics, and this one's probably the easiest one to remember. It's the law of conservation of energy. So the energy of the universe has to be constant. Okay? Remember, the universe is the system plus surroundings. So that means the energy gained or lost by the system has to equal the energy gained or lost or gained by the surroundings. So if the system is gaining energy, the surroundings have to lose that same amount of energy, and vice versa. Okay, and probably easier to understand that in a picture, right? So we have the system is this green circle, surroundings is represented by everything outside of that. So there's a couple different ways that you can transfer energy. Heat and work are the two ways. So if you have the system gaining heat from the surroundings, heat is represented by the small q. That would be a positive value of heat, positive q value. If work is being done on the system by the surroundings, the work is a positive value. Okay? And delta E is just going to be equal to the heat plus the work. If you have a case where the system is losing heat to the surroundings, that Q value is going to be negative. And if the system is doing work on the surroundings, that is going to be a negative value for work. So let's try a first quick practice problem here. So a system releases 300 joules of heat and has 650 joules of work done on it by the surroundings. What is the change in the internal energy of the system? Okay, and remember, we have this little diagram here. The equation delta E equals Q plus W. Okay, so that's what we're going to solve this with. And that's the change in energy of the system. Right, so Q plus W. Right. So if a system is releasing 300 joules of heat, Q is going to be negative 300 joules, right? Because everything's defined based on the system. So if the system's losing heat, Q is going to be a negative value. It has 650 joules of work done on it by the surroundings. So work is going to be a positive number, positive 650. Okay, so delta E is going to equal minus 300 joules plus 650 joules. Right, and when we do that, That's just going to be positive 350 joules total. So that's the total change in energy of our system, and that would be choice B here. I should mention this right now. When we work through these problems, these practice questions in a lecture, you might want to pause the recording and try to work through it yourself, and then hit play and see how you did. Right, so there are two cases where energy is transferred as heat only. Okay. You could have a initial state. In this example, we're just using a beaker of water. Right, very, very simple system to understand. Okay. If we have a beaker of water and it's hot water, right, so the temperature of our system is greater than the temperature of the surroundings. This hot water, we can just sit it out on a bench top, and eventually that temperature of that beaker of water will go down. Right, and what's happening there is the heat is released from that beaker of water into the surroundings. Okay. So we're losing energy of our system, our beaker of water is losing energy in the form of heat to the surroundings. So that Q value for this is going to be negative. Right. The other case you can have is the system absorbing heat, right? So if you have a beaker of ice water, sit it out on a room temperature bench, it's going to absorb heat from the surroundings, and this will give us a positive Q value. Heat's going to go into that beaker, that system. Delta E is going to be a positive value. Right. And why we care about heat flow, it turns out, like in chemistry, this heat flow is really how most of the energy is being transferred. Especially in this class, we don't often consider work being done. Okay. And if you remember back, there are two terms for this depending on which direction the heat's flowing. So if you have a process where heat flows out of the system to the surroundings, or Q being a negative value, that's what we call exothermic process. Right? You can kind of think of exo as being meaning out of, and we're talking about the system, so it's out of the system, and thermic just being heat. Okay. The opposite of that is endothermic, where we have heat moving into the system from the surroundings, and that would be a positive Q value. Okay. So examples of this, if you have water vapor in the air, and it condenses, what's happening there, you're assuming that water vapor is our system. The heat is being released into the surroundings, and then it's condensing into a liquid. That would be an exothermic process. The opposite of that, if you have liquid water and you heat it up to boil it into water vapor, that's an endothermic process. You're supplying heat to that water to get it to change phase. So second practice question, the result of an exothermic reaction is, 1, the energy of the system decreases and the energy of the surroundings increases. 2, the energy of the system increases and the energy of the surroundings decreases. Or 3, the energy of both the system and the surroundings increases because it is a reaction. Okay, so think about that for a second. Well, we can kind of just rule out 3 right now, right? Because the energy of both the system and surroundings can't increase at the same time. We know that from the first law of thermodynamics. Right? So exothermic, what does that mean? It means heat's leaving our system. So for that, assuming no work is being done, the energy of our system has to be decreasing, and the energy of the surroundings has to be increasing. Okay. Again, that's assuming no work is being done, but probably 99% of the time in this class you can assume that. Okay. Bond breaking. Okay, what is bond breaking? What kind of a process is that? Is that endothermic or exothermic? Well, this one can be a little bit tricky. It turns out that bond breaking is actually endothermic, and that's because it requires energy. It requires energy to break that bond. Right, if you think about that potential energy curve when we make a bond, you kind of go down into this valley here of potential energy, okay? Because it's when you form a bond, it's making this molecule is becoming more stable than the two atoms that were apart, okay? And you have to overcome that energy well. You have to supply this much energy to be able to break that bond, okay? So it's an endothermic process. And conversely, to form a bond, you actually give off energy when you're forming a bond. So that would be the opposite, would be an exothermic process. Some things we'll be considering important in this discussion are phase changes. Okay? When we have a solid moving into a gas, or solid to a liquid, then liquid to gas, those are processes that require heat. So those are endothermic processes. You need to supply heat to do that. And the opposite of those, gas to liquid, which would be condensation, or liquid to solid would be freezing. Those are processes that might not be as evident in everyday life, right? But those are actually exothermic processes because they're giving off heat from that system. And then the straight from gas to solid, that's called deposition. Okay? And that's also an exothermic process that gives off heat. Okay. The endothermic direction, probably easier for us to guess or pick or understand, because if you take something solid and you want to melt it into a liquid, you have to supply heat to do that. Not so obvious that when a liquid freezes into a solid, it's actually giving off heat. Right, so those processes are endothermic. Processes on the right side are exothermic. Okay. Now, if we look at the molecular level of this, you can kind of if we're looking at the endothermic processes, solid going to a liquid or a liquid going to gas, where you need to supply heat, right? We can think of this as the absorbed heat is going to increase the kinetic energy of the molecules. The molecules, therefore, will be moving around more, right? So if you have a solid, those molecules are fairly stationary. Once that you supply enough heat, that phase will change. The molecules in a liquid can move around much more freely, and then obviously in a gas, they're moving around really fast. They have a lot of kinetic energy. Okay. If we look at the reverse processes where we're getting heat out, you can think of the loss of kinetic energy is caused by the release of heat from these molecules. So if that helps you remember whether these processes are endothermic or exothermic, that might help you justify it or think about it in your head. Okay. Section 2 in Chapter 6 deals with enthalpy, and that's in this class we're going to be dealing with constant pressures, at least for enthalpy, right? Okay, so what enthalpy is, it's defined as the energy plus PV. And what is PV? That is pressure and volume, and that's really the work, okay? So what enthalpy, you can think of enthalpy, if you remember our equation for energy, energy equals heat Let me just write that again. Energy equals heat plus work. So our change in energy equals heat plus work. Well, you can kind of think of, work is minus pressure volume of our system. And so if we rearrange this to solve for our heat, it's going to be the energy plus work, minus work, but that would be plus pressure volume. Okay, so what enthalpy is actually a measure of heat. Right. Okay. And when we're talking about a constant pressure, it's going to be in this class. We refer to this constant pressure P times delta V. So the volume is going to be what's changing when we're considering work and not the pressure. Okay, but honestly, most of the time we're not going to be dealing with pressures or volumes here. Okay. And for enthalpy, delta H, as with Q, when it's a positive value, we consider that endothermic, and when it's negative, we consider that exothermic. Remember, endothermic, the heat is coming in. Exothermic, the heat is going out. Okay. All right, and we can add subscripts to this, right, to denote what we're talking about. So we can add, the delta H of a reaction, or the delta H of the system, or a specific phase change like vaporization. So you'll see those frequently. Okay. We can use this. Why chemists use this? It's sort of a quasi measurement of the energy of a system. And this is true when the reactions aren't involving gases, because if you don't have gases, you're not changing in pressure or volume. Okay, for reactions that do involve gas, but the total number of moles of gas does not change, this holds true as well. And then for reactions in which QP is much larger than the P delta V, so heat is much larger than work, this actually will hold true as well. The delta H can be a reasonable approximation for delta E. Again, we're probably not going to have to deal with these two cases in this class. You can really assume that delta H is an approximation for delta E in this class. So if we use our little pictures to diagram this out for exothermic and endothermic processes on a chemical level, okay, for this reaction, methane plus O2, oxygen, going to CO2 plus water, so this is a combustion reaction of methane. Okay, our reactants, the enthalpy of our reactants is going to be a higher value than the enthalpy of our products. So the overall change in enthalpy of this reaction is going to be negative. It's going to be less than 0. That means heat is going to be released from this process, and it's an exothermic process. Okay, it's giving out heat. Okay, so this exothermic process gives out heat. Well, this is combustion, right? So it's burning that methane. So that's kind of probably obvious for us in a day-to-day kind of lives, that when you burn something, heat comes out of it, right? That's exothermic. Okay, something, that it's sort of hard to find endothermic processes just off the top of your head. The easiest way to do that is phase changes. So if you go from solid water, which ice, to a liquid, right? You melt that. That process requires heat coming in, right? So the water solid water ice is going to have a lower value of enthalpy to start than the liquid water. So you have to supply heat into that. Delta H, therefore, will be a positive, and that's an endothermic process. You need heat. All right, you can graph these out, these phase changes. And if you graph the temperature versus the heat you have to add into the system, it'll look something like this. So you'll have, let's say we start at negative 18 degrees Celsius, and we're talking about water here, so that would be a solid. Okay? As you start adding heat, that heat is going to go to first raise the temperature of that solid ice. Okay? So as you add heat, the temperature will increase. Then you come to these flat horizontal parts in this plot. Okay, you're still adding heat, right? We're still walking along this axis here, this x-axis, so we're increasing heat, but the temperature isn't changing. What's happening here is your solid water, solid ice, is turning into liquid water. So this right here is a phase change. You're adding heat, you're not changing a temperature, but what you're doing is changing a phase. And if you'll notice, right, to get to negative 18 to 0, we barely added any heat, right? Barely added any heat on this x-axis, and the temperature increased. But look how far you have to walk along this x-axis from point B to point C. That's a lot of heat being added into that without any change in temperature. So those phase changes require a lot of heat, more so than actually changing the temperature. Okay. Once we do change that into a liquid, now we add more heat to it, and that heat then can be used to raise the temperature of the liquid water. Okay, and we do that until we get to 100 degrees, which is the boiling point of water. Then that heat being added into that has to go into changing from a liquid to a gas. Okay. So we can describe these portions of this curve, these slanty portions where you're actually changing the temperature. The heat in is going to kinetic energy of those molecules. Okay. The horizontal part, the heat coming in at these points is going into a phase change. Right. Heat capacity is a term we talked about. All right. There's different types. You can have it in terms of moles, right? The molar heat capacity, small cp. You can have it in terms of mass, which we refer to as a specific heat, or small c sub s. Okay, those are really can be used interchangeably. In the equation for heat here is given Q equals N times the heat capacity times delta T, right? These are used interchangeably depending on what units you're using. So if N is in moles, we would use the molar heat capacity. If your N value is in mass, then you would just use the specific heat. Okay, but they're used identically. Heat capacity with a capital C, that's usually the heat capacity of an object. When we're talking about this, usually it's a calorimeter. So that's just another thing that would have to be taken into account if you're doing a calorimetry problem. Okay. So let's try some practice problems with these. During a strenuous workout, a student generates 2,000 kilojoules of heat energy. What mass of water would have to evaporate from the student's skin to dissipate this much heat? Okay, remember, we have our equation for heat in terms of a phase change here. Q, the heat, equals N, the amount, times delta H of vaporization. Okay, so think about this one. Try to work through it, and we can answer it together. Okay. So we know we're going to use our equation for the heat of a phase change. Okay, and we're given the amount of heat that the student is generating, which is 2,000 kilojoules. So our Q is 2,000 kilojoules. Okay, we're given delta H. Delta H is 40 kilojoules per mole. Right? So we need to rearrange this equation to solve for the N, get the amount of water. Okay. So if we do that, N is going to be equal to Q divided by delta H of vaporization. Okay. And we can solve that, plug our numbers in. So Q is 2,000 kilojoules. Delta H is 40.7 kilojoules per mole. And when we do that math, that will equal 49.14 moles. Okay, so that's the moles. The question's actually asking for the mass, so now we have to use the molecular weight of water, which is 18 grams per mole. So we multiply that by our number of moles that we calculated, and we get something like 884.5 grams of water. All right, so that's, almost a liter of water that would need to be evaporated. Yeah. Okay, so kind of skipping over the third section, calorimetry. We'll just not focus so much on calorimetry. Going into section 4, stoichiometry of thermochemical equations. Okay, so a thermochemical equation is a balanced chemical equation that includes a delta H of reaction. The sign of delta H indicates whether the reaction is exothermic or endothermic. Remember, endothermic would be a positive value, exothermic would be negative value. The magnitude of delta H is going to be proportional to the amount of substance that you have. Okay, so these delta H values of the reaction are typically going to be in kilojoules per mole. So that per mole basis sort of will tell you how much of the reaction reactants that you have. Okay. The value of delta H can be used in a calculation in the same way a mole ratio can be, because it has that per mole basis in it. So here's a relationship between the amount or moles of a substance and the energy transferred as heat during a reaction. So if you have the amount of substance A here, right, in moles, you can convert it into the amount of substance B just using that balanced mole ratio in the balanced chemical equation, right? So we talk a lot about that from chapter 3. Taking it a step further now in chapter 6, what we can do is use the delta H of that reaction, which is in kilojoules per mole typically, right? And convert, the amount of, in this case, let's say substance B is a product, the amount of that's formed, we can multiply that by our enthalpy of the reaction and get the amount of heat that's being released or absorbed by this particular reaction. Okay, so let's try a practice problem with this principle. Okay. MREs, or meals ready to eat, are a type of ration that soldiers use in the field. They are heated with a flameless radiation heater, which uses the following reaction. So we have solid magnesium plus water, so we just add water to that, right? Very easy to do when you're in the field. That creates magnesium hydroxide and hydrogen gas, and this reaction is very exothermic here. You can see it gives off 441 kilojoules per mole. Okay. Right, if it takes 53 kilojoules of heat to warm one of these meals, what is the mass of magnesium that must be used in that FRH in the MRE? Okay. Okay, so this word problem, it might seem on the surface a little bit tricky or confusing, but just try to break it down and go through the dimensional analysis. We're given a value of kilojoules, and then we're given a value in kilojoules per mole. So here, we want to find an amount of something, the mass of magnesium. So we have enough information here to determine the number of moles of magnesium that must be used. Okay, so here's a kind of a roadmap of how to do this. Okay, we have our heat and our delta H. So if you want to remember the equation, it's heat is going to be equal to N times delta H of our reaction. Okay, but if you didn't remember that equation, you could kind of look at what units were given here, right? Kilojoules per mole and kilojoules. Okay, we can rearrange these to get the number of moles. Okay, and so that becomes, right, number of moles is just going to be our heat that was given off, or in this case that needs to be given off, divided by our delta H of our reaction. Okay. And so the heat is 53 kilojoules needed. Delta H is 441 kilojoules per mole. Technically that is a negative number, but it's negative because the system is giving it off. The surroundings is what needs to absorb that. The food is our surroundings in this case, so that's what needs to absorb it, so we can change the sign. Okay, if you didn't change that sign, you would just get a negative value for moles, which, right, that doesn't make any sense. So if that ever happens to you, if you get negative moles or a negative mass, you can just be, that doesn't make sense. I need to change the sign on that. Okay. So here we have 0.12 moles of magnesium. Okay, so here, if we put it on our roadmap, that's 0.12 moles. Okay. Then we just need to convert this into a mass. Okay, so that's all that involves is multiplying by the molecular weight, which for magnesium, it's just the atomic weight is 24.3 grams per mole. Okay, and what we get is 2.92 grams of magnesium. Section 5 in Chapter 6 talks about Hess's law, and this is what the book describes as finding the delta H of any reaction, which, I don't know, it's a little bit misleading, I guess. But what Hess's law states is that the enthalpy change of an overall process is just going to be the sum of the enthalpy changes of the individual steps. Okay, so let's say you have a reaction that you don't know the delta H for, but if you break it down into individual steps and the delta H values are known for those steps, you can just add those up and get the overall. Right, so our example here is if we have methane plus water and we want to find out, that if this reaction here, we want to use the methane plus water going to hydrogen gas plus carbon dioxide, okay, but we don't know that reaction directly here. We can take two steps to get there. So methane plus water going to carbon monoxide plus 3H2, and then this going to 4H2 plus CO2. when we add another water, right? So we can do these 2 steps, and maybe those enthalpy values are known in, you can look those up in a table, let's say, where we couldn't look this one up. We can just add these 2 together to get the enthalpy change of the overall reaction that we're interested in. Okay. So how do you do a problem like this? First, you have to identify the target equation. That's the reaction that you're interested in. The step whose delta H is unknown. Note the amount of each reactant and product, okay? And then you manipulate each equation with known delta H values so that the target amount of each substance is on the correct side of the equation. So you're trying to, in a Hess's law problem, you'll typically be given like a few different chemical reactions. You just have to manipulate them so that you can get things that end up on both sides of the arrow to cancel out, to give you your target equation, the reaction that you're really looking for. Okay. And to do that, you change when you have to flip a chemical equation, you change the sign of delta H. And if you have to multiply by a certain amount, let's say you have an equation where there's 1 H2O in it, but you need it to have 2 H2Os to cancel out with the 2 H2Os on the other side of an arrow in another equation. You multiply through by that amount too, let's say. You'd have to multiply the delta H as well by that same amount. Okay. You add these manipulated equations together. They add up to your target equation. Then you would also add the delta H values together to get the delta H of the target equation. Right. All substances except those in the target equation must cancel. So this, explaining it in words is probably a little bit hard. It's probably easier to just go through one of these examples. So if we use Hess's law here to sum up the enthalpies, let's say our first equation is CH4 plus H2O going to carbon monoxide plus 3H2. We'll call that H1, delta H1. Right. Our second step there was CO plus 3H2 plus H2O going to 4H2 plus CO2. Okay, that's delta H2. Right, we can cancel out things that are on both sides of the arrows. Right, so CO and 3H2 were the same in both of these equations, just on different sides of the arrow, so they will cancel out. Okay, what we're left with would be CH4 plus 2H2O goes to 4H2 plus CO2. And remember, that was, in that example we were using, that was our target equation. Okay, so that enthalpy for that, delta H3, would just be equal to delta H1 plus delta H2. Right, so if we use trying to do these calculations, right, in getting the rule straight, remember, if a reaction is reversed, the delta H sign of that reaction changes. So for the reaction N2 plus O2 goes to 2NO, that delta H is 180 kilojoules. If we have to reverse that, let's say we're doing a Hess's law problem and we have to reverse that, we would have to reverse the sign, change the sign of that delta H. So the reverse reaction, the delta H is negative 180. Right. And again, if you have to multiply through by a certain coefficient, you also have to multiply the delta H by that coefficient. So let's say we need to multiply this reaction by 3 to get 6NO goes to 3N2 plus 3O2. Well, then we'd have to multiply the delta H of that reaction by that same factor, by 3. Okay, so let's try a practice question using Hess's law. Okay, so here we have three equations, okay, and we have to get these to add up to our target equation, which is given up here on top. All right, so this equation up on top. To do this, there's no real rule that you have to follow, so you kind of have to just do this by inspection. So if I look at this first equation, H2 is on the correct side of the arrow that it's in our target equation. So I'd probably just want to leave that one how it is. All right, so H2, same side of the arrow as it needs to be in this. So if we just left that, let's see what that looks like. If we look at this equation, second one, C2H4, it's also on the same side of the arrow that it is in the target. And it has the same coefficient, a 1 out in front of it. So that's probably okay to leave. The third equation, however, if we look at that, C2H6 needs to be a product in our target equation. And in this equation, it's given as a reactant. So this is one we're likely going to have to switch. Right? So we need to write that in the reverse direction. So just ignore this one now. We rewrote it in the reverse direction. And when we did that, we flipped the sign of our delta H. It went from a negative to a positive. Okay. So now we can, if we want to see what cancels out here, we would have 1 H2O and plus 2 H2Os on the product side. They would cancel out with the 3 H2Os on the reactant side here. We have 3 plus 1/2, so 3.5 oxygens on the reactant side. They would cancel out with these 3.5 or 7/2 oxygens on the product side in this equation. And then finally, 2 CO2s would cancel. Okay, so what we'd be left with when we did this, everything that's left would be C2H4 plus H2 goes to C2H6, right? And that is what our target equation is. Right, so then we would just add up all these delta H values, right? We'd sum those up. And when you do that, you should get the delta H of our target reaction as minus 136.8 kilojoules, or kilojoules per mole. Okay. The final section in Chapter 6 talks about the standard enthalpies of reaction. So here's another way of calculating the delta H of a reaction. And honestly, it's probably an easier way than Hess's law. Right? The standard enthalpy or the specific enthalpy of a process can be determined. So the standard enthalpy of formation is something we use to describe the formation of a particular molecule, right? And it's denoted as a delta H. F stands for formation, and the naught just means it's at standard conditions. Right? So you can determine these for everything in a sense. So it's the enthalpy change of the formation reaction. And what is a formation reaction? It is the process of forming 1 mole of the substance in its standard state from its elemental components in their standard states. Okay, so that might seem a little bit maybe confusing or challenging. You probably don't need to remember this. We'll see using these standard enthalpies of formation, they are values that you look up in a table. Okay. Right. But if we use water as an example of this, what is the formation reaction of water? Well, we have a reaction that makes 1 mole of water from its elemental forms or component elements. Okay, so that would be hydrogen and oxygen. And their elemental forms are as diatomic gases. So H2 plus 1/2 of O2 goes to H2O. Okay, so that's pretty easy. When we say the delta H of this reaction, that would just be the delta H of formation of H2O, right? By definition, this is a formation reaction. Right, the standard state of a substance is the most stable form at 1 pressure of bar and at 25 degrees Celsius. If we depict this in a picture, what this would look like is, okay, so we have reactants, and they have a particular enthalpy value, right? If we break them apart, the decomposition of them, so if we break these reactants apart into their constituent elements, that would be a negative delta H of formation for those, okay? And then we use those elements to produce products. Their delta H, we'd use the positive value of their delta H of formation to determine that for the products. And then the difference there between the two reactants and products is our delta H of reaction. All right. So mathematically, we can represent this. The delta H of reaction is really what we're concerned with, right? Going from reactants to products. But if we can't measure that directly, what we can do is look up these values, delta H of formation, for the reactants and for the products. We can look those up in a table, and then we use this equation. It's just going to be the sum of delta H formation of the products minus the sum of delta H of formation of the reactants. Okay, remember deltas are products minus reactants, or final minus initial. Okay, that holds true here. The M and the N, those are just the coefficients from the balanced chemical equation. So in our balanced chemical equation, if we have a 2 in front of one of the molecules, we're going to have to multiply the delta H of formation for that molecule by that factor, by 2. Okay, so probably easier to just go through a problem of this instead of trying to talk about it. So problem 7, we're using our delta H of formation values to find the delta H of reaction. Okay, and we're given this reaction again, CH4 plus O2, so the combustion of methane going to CO2 plus water. Okay, so we just look up these delta H of formation values, right, for our products and reactants. So our products would be CO2, which if we look that up, that's right here. And also need to point out, the state of matter really does affect it. So in this example, we have CO2 gas. So we need to make sure that the value in the table is for the correct state of matter. So here is CO2 gas. It really comes into play a lot when you have water in this in your equation, because water will have 2 values, usually one for gas and one for liquid. So and they're different, right? So you need to make sure you're getting the right one. Right. So for H2O, we're going to need to look that up as the liquid water, because that's what it's denoted here. So that'd be negative 285.8. Okay, and our reactants are methane gas, which is here, and oxygen gas, which is up here. And for elements that are in their standard molecules, I should say, that are in standard elemental form, like O2 here, the delta H of formation is just going to be 0. Right, so if we did all those values, right, our delta H, let me switch to my pen. There we go. Delta H for that reaction is just going to be the sum of delta H formation of products minus the sum of delta H formation of reactants. So in this example, right, we had so I'm multiplying through by the coefficients. So for CO2 we had 1, for H2O we had 2. So CO2 we're multiplying by 1. You can, if you wanted to keep the units in this, that would be 1 mole, right? And then our delta H of formation for CO2 is 393.5 kilojoules per mole, right? So the moles technically cancel out, and our answer is going to be in kilojoules, right? So H2O, there's 2 times minus 285.8. Okay. And important to note that these brackets at the end, so this whole thing, we need to do that math first before we do this math, right? This negative sign. Okay, so our reactants were 1 mole, right? 1 mole of methane and 2 moles of O2, right? So methane had a delta H of formation of minus 74.8 kilojoules per mole, right? And remember that coefficient out there is in moles, so those cancel. And then oxygen had 2 moles, but its delta H of formation was 0, so we really don't need to consider it, right? It goes away. Right, so when you're entering this in your calculator, just remember you have to do all those values separately. Very easy to forget a bracket in one of these problems, and then you get a number that's completely different. You go back and look at your work, it looks like you're doing it right, but you're just entering it in your calculator incorrectly. So this would be 965.1 kilojoules minus a minus 74.8 kilojoules, which would be negative 890.3 kilojoules. Okay, so last problem, let's try another one of these. Okay, one step in the production of nitric acid is the combustion of ammonia. Use the data below to calculate the enthalpy of this reaction. Okay, so we have 4NH3 plus 5O2 goes to 4NO plus 6H2O, right? And the values that we need are shown in the table, the delta H of formation values. So again, we're going to use our delta H is equal to the sum of the products minus the sum of the reactants. Right, so our products were, we had 4 moles of NO, and the delta H of formation for NO was 90.3 plus 6 moles of H2O, and that formation, delta H, was negative 241.8. Again, those numbers are in kilojoules per mole. The coefficients are moles, so we're going to get kilojoules out when we do all this math. I'm just not including them for interest of saving space here. The reactants were 4 moles of NH3, which was a formation delta H of 46.1. And then 5 moles of O2, which again has a delta H of formation value of 0. Okay. So when we do this math, 4 times 90.3 would be 361.2, plus 6 times negative 241.8 would be negative 1450.8. Right, so we do that first, then we would subtract a 4 times negative 46.1, which would be negative 184.4. So again, a negative of a negative, we're going to get basically be adding that. This would be negative 1089.6 minus negative 184.4. When you do that, should get something like 905.2 kilojoules. Okay, so just in summary, there's 3 ways we learn about in Chapter 6 of determining the delta H of a reaction. One was from calorimetry experiments, which I didn't go through in this lecture, which we won't really be doing in this class. 2 is using Hess's law, okay, and that's summing up the delta H of reaction of a series of reactions that will equal the reaction of interest. And then 3 is probably the easiest way, and honestly, moving forward in Chapter 20, when we're calculating the delta S of reaction or the delta G's of reaction, this is the way that we're going to be using this same method to calculate delta S's and delta G's in Chapter 20. And that's from the enthalpies of formation, where you have the sum of the products minus the sum of the reactants. Okay, and again, all those delta H of formation values, those are in the back of the book in the appendix. So you just look those up. Okay. So next lecture, we're going to talk about when a reaction is spontaneous, and how we determine that is by entropy and the second law of thermodynamics.